is additive manufacturing lecture number 6. So we have been talking about the benefits of additive manufacturing and the distinction between additive manufacturing and CNC machining. And we started talking about photopolymerization techniques, which is the basic methodology that is used for stereolithography. In this class, we will talk more about the different kinds of materials, resin formulations, and reaction mechanisms. And we will also talk a little bit about um, extrusion-based processes, mainly for special type of materials such as ceramics. So, what kind of polymerization materials, photopolymerization materials that we can do? Mainly, they have to be polymers that can be cured by gamma rays, X-rays, electron beams, UV, and in some cases visible light. But gamma rays and X-rays means they have to be protected quite a bit. You have to protect yourself, and it is not easy to do, especially in a shop environment. So, what you would find is that they are mostly UV based um, or electron beam that is used for um, curing these resin systems. For example, SLA 250 is one of the earliest 3D printing techniques made by 3D systems. They use a helium cadmium laser with a wavelength of 325 nanometers, and that wavelength is dependent on the resin system because the wavelength can provide you with energy. So the general trend is that shorter the wavelength, higher the energy. Okay, so here is a YouTube video that you might want to take a look at. Um, and um, in the case of there is a technique that we call DMD. DMD is direct manufacturing something. So UV and visible light radiation are used. So what do you have in these photopolymers? They are composed of several types of ingredients. They have photoinitiators, they have reactive materials that are added to reduce the viscosity of your material. Then you have flexibilizers so that the material is flexible as soon as it is made, but after it is made, if you um, do curing, post curing at an elevated temperature, then it can become hard and strong. Then you have stabilizers, and you also have liquid monomers. So what happens to this resin system when it is exposed to UV radiation? When it hits the resin system, the photoinitiators in the resin system undergo a chemical transformation and become reactive with the liquid monomers. And then that once it becomes reactive with the liquid monomer, it starts a reaction with the monomer molecule to start a polymer chain. And then it keeps linking up and becoming a large chain and stronger chain. So depending upon the type of reaction and chain that is formed, you get different kinds of properties. So for example, you have two main types of polymer chemistry in these photopolymers. One is there is a if you have acrylate, it undergoes what is called a free radical photopolymerization. If you have an epoxy type of resin, then you have a cationic photopolymerization, mainly in the case of epoxy and vinyl ethers. And these are the molecular structures of these reactions. And you can find that this one is a reasonably long straight chain, and then we can link up with other molecules to make the whole reaction go. The epoxy and the vinyl ether are not as complicated as the acrylate, but they are equally strong. So the acrylate photochemistry was the first commercially developed stereolithography resin, and they form long polymer chains once the photoinitiator becomes reactive. It starts building the molecule linearly by adding monomer segments. And once those monomer segments get linked up, and depending upon the angle at which that reaction is present, or the additive chain is present, it can be strong or not as strong. And the one big advantage with the acrylate photopolymers is that they are extremely fast to react when exposed to UV radiation. So once the reaction takes place very quickly, it can undergo significant shrinkage and warp and curl after reaction. So in order to reduce the amount of shrinkage and warp and curl, now you also add epoxy additives to these kinds of resin systems. So the new types of resin systems are more epoxy based. They are epoxy based cationic photopolymers. And when they react with the UV light, those epoxy rings open up, resulting in sites for other chemical bonds to come and join them. And in this case, the ring opening reaction is not as um, resulting in shrinkage or some kind of changes in the whole structure. So because you do not want residual stresses to be introduced into your part, so by doing the epoxy based cationic photopolymers, you can get a stereolithography resin system that does not shrink as much as the acrylate type of resin systems. And the number and types of chemical bonds are essentially identical before and after the reaction. So the current commercially available stereolithography resins have significant amounts of epoxy backbones, which was not the case in the early 90s or the mid 90s. Now, one thing to note is that when you polymerize these stereolithography monomers, it is an exothermic reaction, and that heat of reaction can be around 85 kilojoules per mole for an acrylate monomer, but that's different in the case of the epoxy based resin systems. But even in spite of this high heat of reaction, you do need a catalyst to initiate that reaction. And in this case, you have a photoinitiator that can act as the catalyst. So this is a schematic of that whole reaction. So you have a system where it is free radical initiated polymerization process, and for and what is the whole purpose of hitting them with a laser beam? The laser beam provides two photons for I mean provides photons for the reaction itself, and for every two photons that are delivered to the resin system, there will be one radical that will be produced. So you can see this one. So once the laser hits the monomer, it creates a free radical, and that free radical plus the monomer uh, forms it starts initiating, and then those free radicals will then just link up and start polymerizing. So it propagates a reaction, and then you end up with a terminal reaction. So now you have a length polymer chain of length so and so, which is ending. This can be in different directions. So depending upon that, you can get different kinds of properties. The pi term is the photoinitiator, and the I star is a free radical, and M is a monomer. So one reaction or one free radical can easily result in the polymerization of over 1000 monomers. Now, how do you end this polymerization? It terminates from one of three causes. It's called recombination, disproportionation, or occlusion. Recombination occurs when two polymer chains merge by joining two radicals. And disproportionation is essentially these radicals have opposite signs and they cancel out each other without joining. And in this case, the free radicals become trapped within a solidified polymer, meaning that the reaction sites remain available, but it doesn't go any further. The reaction doesn't go any further. And most of the time, you end up with a limited mobility within the polymer network, so the reaction has to stop. But this can also lead to properties that are not good for this resin system, which is it could cause aging or creeping in the future. Cationic photopolymerization is the same broad structure as a free radical polymerization. So it generates a cation as soon as the laser beam hits the resin system. It then reacts with the monomer, and then it propagates to generate a polymer, and there is a termination process completing the reaction. So, and you need a typical catalyst for a cationic polymerization, which is a Lewis acid. They call it BF3. So let me stop here for this section of um, lecture, and then we can continue it in the next one.